Hi class, in this last part of Chapter 4 we're going to talk about gravity a little bit more and energy and how we can understand orbits of planets and also how we can understand tides, how the moon and the sun kind of cooperate or even work against each other to create the tides. And then also at the very end we'll talk a little bit briefly about why do objects fall at the same rate. So we've talked about this before, and you can see videos of this, of an astronaut dropping a feather and a hammer on the moon, and both the feather and the hammer fall at the same rate. They hit the ground at the same time. And so we'll say a few things about that. So when we talk about orbits of planets, here's the sun and here's a planet, and this could apply, what we're going to say here applies to any kind of orbital system, any kind of star or planet system. And we've talked before about conservation of energy, conservation of angular momentum, and also conservation of momentum. And both conservation of angular momentum and conservation of energy are things that are useful to think about when we think about planets going around a sun, any star. So, if you remember, gravitational potential energy is an energy of interaction between two objects that have mass. So, in this position, the planet is close to the sun. And so when the two objects are close together, there's lower potential energy. There's lower gravitational potential energy. And the planet here has some speed. It has some velocity. And so it has some kinetic energy. So when we add the kinetic energy and the potential energy together, we get what's called the total energy, the total orbital energy. And so when the planet then is moving, as the planet moves, it is moving in this direction at this point. And so it's not going to keep going in this direction. The gravitational pull from the star is going to pull it this way. And so instead of going straight this way, the planet curves. And if the planet has enough speed, it could get further away from the planet, or further away from the star. So what happens as it gets further away from the star? Well, remember with gravity, if you get further away from something, the gravitational potential energy increases. It goes up. So if the total energy is gravitational potential energy plus kinetic, and this total energy is what we call conserved, it is constant, then if this gravitational potential energy is going to get bigger, that can only happen if kinetic energy gets smaller. So if the planet has an orbit around a star that takes it from a really close distance to a further away distance, as it moves further away, the potential energy gets bigger, and therefore the kinetic energy must get smaller. So when the planet ultimately gets to its farthest position, the kinetic energy must be the smallest. In other words, the velocity must be the smallest. So again, kinetic energy is related to velocity. It's actually related to the square of the velocity. And so this can be understood, this idea that the planet moves slower when it's farther away and faster when it's closer, can be understood through conservation of energy. And conservation of angular momentum as well is also useful, but it's just another way of almost seeing the same thing. So we'll just focus on energy here. So that's a thing to keep in mind, just to kind of remember that conservation of energy reminds you, or should kind of tell you, that the closer you get to a star, the lower the potential energy is, and therefore the higher the kinetic energy will be, and therefore the faster the planet will move. Here's an example of how you can change an orbit of a planet, or a comet, or whatever it might be that's going around something. So this shows some objects going around the sun, a comet in particular as well as Jupiter. And here's the path of the comet, and this dotted line is the path that it would have normally taken. But because of an encounter with Jupiter, if Jupiter just happens to be in this position, the comet, as it gets closer to Jupiter, starts getting pulled toward Jupiter. So that's going to change the energy of the planet, of the star comet orbit. Jupiter interacts with it a little bit, changes the energy of the comet's orbit, and so the comet doesn't go along its normal orbit, but rather it goes along a different orbit. And that different orbit in this example just happens to be something that makes it go kind of in the opposite direction now. So rather than going this way, kind of around the star like that and then up, the comet actually goes the other direction around the star. So this is just one example of many possibilities of things that could happen when a comet or any other object has a gravitational interaction with another body in the solar system. And that's when we talk about the formation of the solar system, we'll talk about how the planets formed and why we see comets in certain places. And one of the ideas is that early on in the solar system, because Jupiter is so big, it had a lot of gravitational encounters with various bodies that were orbiting the star, kind of close to the star, close to our sun. And all those gravitational encounters, or a lot of them, took those comets, and instead of making them have a smaller orbit around the star, Jupiter actually kind of flung them out and made them have a much bigger orbit around the star. It gave them kind of a gravitational assist, kind of added some energy to them. So both things can happen. You can sort of capture a comet. In fact, this orbit here, originally, this orbit might have been an orbit where the comet was just going to go on and never come back again, one of those hyperbolic orbits we had mentioned before. And so because of this gravitational encounter, the comet has been trapped in an orbit around the star. Again, whereas otherwise it would have maybe gone on forever and never came back again. So that's a possible thing that could happen. Other things that could happen are if a planet or, say, a satellite around the planet, like the Earth, gets too close and it encounters the atmosphere of the planet, we can change the orbit of that satellite through friction, basically, or what you might call atmospheric drag. So that's another way to change the energy of an orbit, and then that would then change the shape of the orbit. So there's also something, and I mentioned this a little bit in a previous lecture, but something called escape velocity. If you launch something away from a planet, there's a certain minimum speed that you have to give that thing for it to completely escape. And by that I mean so that it just never comes back again. Technically, because the force of gravity can go on forever, you technically can never get away from the force of gravity of anything. But if you have enough kinetic energy as you're leaving something like the planet Earth, you could have enough kinetic energy that it will just keep going and going and going forever, even though there might be still a really, really tiny force trying to pull you back toward the planet, toward the Earth, for example. You'll still have enough kinetic energy that you'll never actually come back. So that minimum velocity you need to have as you're launched from a planet is called the escape velocity. And for the Earth, the escape velocity is around 11 kilometers per second. So that's pretty fast. So there's a couple little animations related to this that I wanted to show you. One is, I think I'd mentioned these before, if you go to, even if you just Google Phet, these are a bunch of simulations, some of them written in Java, some of them written in HTML5, and those HTML5 ones should run pretty easily in your browser. But this is an example of one called Gravity and Orbits. And it starts off with a star that makes it look kind of realistic. The star is sort of small, the planet is even smaller, and we're kind of looking at this system from very far away. And right now we've got it set up so that we have a star that's the same mass as our sun and a planet that's the same mass as the Earth. So what I'm going to do is turn on the path so we can see what the path looks like as the planet goes around, and I'll hit play. And so it shows the planet going around the star. The mass is the mass of the Earth, and we're counting off the days here. So we can see the planet going around, and there's about a half a year there. We'll come around here, and we'll try to change a few things. Let's wait for it to do almost one complete orbit. So it's going to come along. It's going to come right back about where it started, right through that point. It looks like a pretty nice consistent orbit. So let's change the mass of the planet and see what happens. Let's make the mass twice what it is. Let's just see what happens. So I made the mass twice what it was, and what do we notice? Do we notice anything happening? Doesn't look like anything happened. So if we analyze orbits of planets, or orbits of, let's say, satellites going around a planet, or a small object going around a big object, the orbital properties, the orbital radius, the orbital speed, does not depend on the mass of the planet. So this planet could be any mass you want it to be. If it's at a certain distance, it's going to have a certain orbital velocity. That was one of Kepler's laws, if you remember, that the distance, the orbital radius of a planet's orbit was related to the period, the time it takes to go around once, and not necessarily related to the mass of the planet. That's definitely true if you have a planet that is really small in mass compared to the star that it's orbiting. Now what happens if we change the orbit of our star? Let me bring the Earth back to its normal mass. Let it orbit for a second, and let's increase the mass of the star. And let's wait for a second and see what it does. Oh, you can definitely see that the orbit has changed. So the orbital properties are definitely dependent on the mass of the star. And so by increasing the mass of the star, we've definitely changed the orbit, and now it's much more elliptical rather than circular. So now we've got a planet going around the star in a more elliptical orbit. The star is off-center now. The orbit is not circular. And now let's take the star and make it come back to its original mass. And let's see what happens. So now the planet goes out. Oh, and might not even come back now. So what we had done when we increased the mass of the star was we suddenly kind of gave the system some extra energy, and that increased the energy of the whole system, the orbiting planet as well as the star. And when we brought the star back to its regular mass, that system still had that energy, and so the planet went zipping away with a higher speed, and it may have attained like an escape velocity. The simulator doesn't really tell you what's going to happen. We just have to wait around to see if it ever comes back. So we won't do that though. But you can play with this, and you can play with a star and a planet. You could play with a star, a planet, and a moon, just a planet and a moon, a satellite and the moon and the Earth, for example. And you can change various things and look at masses and stuff. So this is a fun little. See, oh, there it comes. Here comes our planet. It's a really big orbit. So it's going to come around again and swing back and go off. So we've really changed that into a really, really big, highly elliptical orbit. Let's zoom out a little bit, see if we can actually see it. Yeah, there's the orbit there. Kind of comes way out here, really far away. So that's a good little simulation, a fun little thing to play with. Then your book has some interactive figures, and some of these are from the older edition. They're changing some of the interactive figures and putting them in some of the simulation, or the tutorials that you might have seen. But this one is similar to what we've looked at before. This is where you have a cannon that you're just going to fire, and you're going to launch the cannonball at various speeds. And so we can launch it at 5 kilometers per second. We'll load it, fire it, and the cannonball just lands in the ground in the ocean or something. So the cannonball crashes to the Earth. If we increase the speed, let's say to 9, reload it, it goes around and it actually orbits, and let's see, it'll come back right through the cannon again, assume that it can kind of go through the cannon, and it makes a nice elliptical orbit around the Earth. So this is a 9 kilometers per second will put you in orbit, but you won't escape. You won't escape the Earth. If we change this to 10 kilometers per second, reload and fire, again we'll be put into orbit and we won't escape. But notice how the orbit gets bigger, and the planet's able to get, or the cannonball is able to get further and further away. And then eventually it comes back though. So it takes 257 minutes to orbit the Earth. Of course, that's not the time that you're seeing it, but and now if we increase this to 11 kilometers per second, we'll fire, and it'll just tell us what's going to happen. But at this speed, the cannonball will take about 2,056 minutes to orbit the Earth. So it's getting really, really, really far out. And it's going to take 165 seconds in this simulation, so we're not going to wait for it. Let's change the speed to 12. Reload, and then fire and see what it tells us will happen. Oh, now it says, the cannonball will escape into space, never to return. So a little over, somewhere between 11 and 12 kilometers per second is the escape velocity of any object being launched from the Earth. That object can be a cannonball, could be a rocket, could be a golf ball, could be anything. This other simulation's a good one about the tides, so we'll look at that in just a second. So let's go back. So another thing we can try to understand with gravity is the tides. How do the tides operate? And so if you look at the Earth, think about the Earth as being a ball with oceans on it. And the oceans are kind of squishy, right? The oceans can be kind of formed and deformed and so on because it's just water and you can make it take different shapes. But the ground is kind of hard and rigid and it's rocky. It doesn't deform as well. So when the moon is over here orbiting the Earth, there's a gravitational pull from the moon on the Earth. But the water on the side of the Earth that's closer to the moon gets a stronger pull on it than the Earth itself does. And the water on the far side gets a weaker pull. So if you think what this is called is differential gravity. There's differences in the gravitational pull across the Earth because of this difference in distance. The near side gets pulled harder, the Earth itself gets pulled but a little weaker, and the other side, the far side, gets pulled but also a little weaker. And so overall what this causes to happen is it causes, in a sense, the water over here to kind of rise up, and the Earth to kind of move up beneath it, but this water to move a little bit as well, but to kind of be left behind. So it ultimately causes this bulge of water, and this is highly, highly exaggerated here. Very highly exaggerated. It's nowhere near this big. But it causes a bulge of water that sort of lines up with the moon. It's not quite exactly lining up with the moon, as we'll see in a second. Okay, but so as the Earth rotates, as the moon kind of stays in this position, it moves around the Earth, but over a course of a day it moves a little distance. But the Earth rotates once in the course of a day. So the tides, how the tides happen is, as the Earth rotates, it's in a sense rotating kind of underneath this bulge. As this ocean here moves into this region, this ocean starts to rise up as it moves into this region. And so this region here will start to get high tides as this region rotates into this position here. The oceans in that region will get kind of pulled upward, and you'll see high tides. And as the regions kind of rotate around into this part of the configuration of the Earth and the Moon, the oceans will not get pulled as much. They'll actually go a little bit lower, and you'll get low tide. But as those regions rotate on the opposite side over here, again, you'll get a high tide. So you actually get a high tide and a low tide twice a day as the Earth rotates around. So the sun has an effect as well. And when there's a new moon and a full moon, the sun is also pulling on the Earth. And the sun also will pull on this ocean, this nearer side, stronger than it'll pull on the far side. The sun will also cause a tidal bulge. But these kind of gray double arrows indicate that the sun's effect, the effect of the sun, is smaller than the effect of the moon. So these black arrows are the effect of the moon. The tidal bulge caused solely by the sun is smaller than the bulge caused by the moon because the sun is a lot further away. The sun is bigger, more massive, definitely, but it's a lot further away. And with this idea of differential gravity, distance is critical. Distance is really important. So the moon has a bigger effect because it's closer, much closer. The sun has a weaker effect. Even though it's more massive, it's much further away. But when you have a new moon or a full moon, the effect of the sun and the moon kind of add together. These two double arrows kind of reinforce each other. When you have a third quarter or a first quarter moon, the double arrow of the sun is perpendicular to the double arrow of the moon, and the effect is to kind of cancel each other out. So the high tide bulge here and here is not as big as it is when it's in a new moon or a full moon phase. So there's names for these things. When you have a high tide and you have a new or a full moon, we call those spring tides. It's just a name they give them, spring. It has nothing to do with the season spring. All right, just called spring tides. It's almost like the water springs up even higher. All right, so those are called spring tides. And when you have a third quarter and a first quarter, when the high tides are really low, then you have what's called a neap tide. Neap tides occur on the first and third quarter of the moon. So this other little simulation shows we can play this and see how this works. And you'll notice that here's the moon. We've paused it here. Here's the moon. Here's our tidal bulge. And this blue line goes through the bulge. Notice how it's not lined up directly with the moon. This gray line is the differential gravitational effect sort of for the moon. The red is due to the sun. The sun is over here somewhere. But the tidal bulge is not lined up exactly with the moon. And the reason for that is because the Earth is rotating. So the Earth is rotating kind of under this bulge. And what that does is it causes the bulge to kind of be dragged forward a little bit ahead of the moon. So it isn't pointing, this bulge isn't pointing directly at the moon, but rather it's pointing a little bit ahead of the moon. And that drag causes a couple things. It causes the Earth to slow down in its rotation. So over the course of several years, many, many years, the Earth's rotation is slowing down. And it also causes the moon to orbit further and further away from the Earth by a very small amount. I think it's something like 1 centimeter per century or something like that. But it's not a huge effect, but it is measurable over a long period of time. So let's play this and just see what this looks like. So there's the Earth rotating like crazy because we're playing it kind of fast. You can see the days go by down here. And you can see that if I pause it in this phase right about there, this is a first quarter moon, and you can see that the bulge is somewhat symmetric. It's not too terribly bulged. This would be the low tide area, this would be the high tide area. If we let that continue until we get to about, we'll go to a full moon here. So notice how that bulge is getting much bigger right there. So a much, much bigger bulge now. These would be your spring tides. Much lower low tide, or much higher high tide. And so we can continue to let it go around. Whoops. Let's just do that. Okay. So you can see it going around. There's the sun over there. And see the position of the sun is changing because the Earth is orbiting the sun. And as the Earth orbits the sun, the moon orbits the Earth, and the Earth rotates underneath this tidal bulge. So these are good little things to play with, and these should be available. If they're not in your textbook, they should be available in our course's D2L site. So let's go back. One last thing to look at. So this is again the picture that we just saw, how the tidal bulge is not lined up directly with the moon, but it's kind of ahead of the moon. So the Earth's rotation is slowing down, and also the moon is moving slowly away from the Earth, very slowly away from the Earth. So one last thing, question is, why do things fall at the same rate? So the way to understand this requires a little bit of physics, a little bit of math. So earlier on we talked about Newton's second law that says that the acceleration of an object is given by the force that is acting on it divided by the mass of that object. So if you think about a rock falling without any air resistance, assume it's just falling in a vacuum on the moon, for example, or this is technically on the Earth because we've got the Earth in here, and the mass of the Earth is in here. But if there was no atmosphere, then as a rock falls, it just has a force of gravity acting on it. If we divide that force by the mass of the rock, we get the acceleration of the rock. Well, the force of gravity, though, is given by Newton's law of gravity, which is this constant g times the mass of one object, the Earth, times the mass of the other object, the rock, divided by the radius of the Earth. In other words, divided by the distance between the Earth and the rock, between their centers. So we talked about how Newton's law of gravity depends on the distance between the centers of the object. And for an object near the surface of the Earth, that distance is basically just the radius of the Earth. So if we plug this force equation into this up here, we're going to take this thing and just divide by the mass of the rock. If we divide by the mass of the rock, it cancels out the top and the bottom. And so that's shown right here. And all we get is the acceleration of the rock is equal to this number right there. And that number right there, we could calculate it, is about 9.8 meters per second squared. That number doesn't depend on the mass of what is falling. It does not depend on the mass of the rock. So we could have talked about the mass of the rock, or we could have talked about the mass of a person, or we could have talked about the mass of a tall building, I don't know, something that's falling. Hopefully not a building, but a hammer and a feather, mass of a hammer, mass of a feather, two very different masses. But when you calculate their acceleration using the force of gravity, the mass of whatever is falling cancels out. And you're left with an acceleration that does not depend on the mass at all. So what this does depend on, though, is that there are sort of two masses, in a sense. When you use Newton's second law, the mass that you plug in is technically called the inertial mass of the object. When you use the gravitational equation, this is called the gravitational mass of the object. And it wasn't really understood until Einstein came along. Einstein tried to kind of help us understand why this might be true, and experiments have been done to try to verify this, but the gravitational mass of a rock, of a plant, of whatever, anything, is the same as the inertial mass. So it seems strange to think that there are two different types of masses, but technically these two masses take on different roles. One is a mass that allows you to calculate a force of gravity. The other is a mass that allows you to calculate an acceleration. Those are technically two different things. But experiment has shown, and Einstein has been able to explain why, that these two masses are the same. So as far as we can tell, they're exactly the same masses, and that's why they cancel out. So that's why things accelerate at the same rate. So what have we learned? Well, we talked about total energy being conserved in an orbit of a planet going around a star, for example, and that helps us understand why a planet moves much faster when it's closer to the star and much slower when it's further away. We talked about how gravity causes tides and how those tides can be kind of reinforced or sort of canceled out by the effect of the sun. And so we have spring tides and neap tides. And then we also talked about why objects fall at the same rate. So have a good night, and we'll see you in Chapter 5.